squared. Everything about that is nice, right? This is an integrable function. I can find any definite integral based on this integrand. But there is no formula for an antiderivative. There are at least no formula that's what's called an closed form representation. There are formulas, but the way you have to write them, they have some limit or infinite part in them that you can't just do by hand. There's no reason you should know that, other than that tells you how hard this could be. You can easily find a derivative, right? That's why we have rules for finding the derivative of this type of function. We go in the opposite direction, we can't do it. Which is weird, because if you do this antiderivative is e to the x squared plus c. If I put an x in there, it works instantly. Even bigger issue. Y'all know what e to the negative x squared looks like? It's based on what would be the normal distribution in statistics. You ever heard about normal distribution? Or if you want to calculate probabilities in statistics based on a normal distribution, which is like the fundamental idea in statistics, you have to be able to calculate this definite integral. Except for the same reason this one doesn't have one, there is no. So we would say this, but then f is unknown. And it has no closed form. I shouldn't say unknown. We can write a formula for it, but it's not a closed form formula. Usually it has an infinite sum already built into it. Which doesn't make sense to have an infinite sum. This was actually defined as infinite sums. So the fact that if you write this, it must have an infinite sum. Not necessarily surprising. Not saying you know what that is or how to do it, but it shows up. It's a kind of deeper level result. All of statistics is built off knowing these values, but we can't do it using the shortcut. You basically have to draw rectangles and take limits. You might take stats in high school or before. You remember looking in the back of the book and it just had big tables of values? What do you think stats? You ever look in the back of the stats book? There are just huge charts of numbers. And the reason is it's telling you what all the values of this would be if you change A and B. And they're not exact values, they're computed values. Because there's no formula that you can just use for that problem, all they can do is say, if you make A and B this is basically the answer. Here's lots of answers for lots of A's and B's. And they record all these as a big table. As a consequence of this issue, stats books just have go to the back and just have charts and charts and charts of numbers. And it's all because you can't do this. Basically, they have to do a Riemann sum and figure out what is the basis of the answer using a computer. Right? So that's the big kind of takeaway at high level. This is supposed to kind of illustrate how the fundamental theorem works. And the idea, let's say I want to find this definite integral on the left. This says I need to do f of b minus f of a. So this one took me a while to figure out what this is even doing. It says you need an antiderivative, right? What's true about an antiderivative? If you move it up and down, did that change the fact it's an antiderivative? If you move the graph on the left or on the right up and down, does it change the slope ever? So this website does this thing where whenever you plug in the number a for the antiderivative, you get 0. So what they're saying is choose that constant so that when you plug in the number a, you get 0. So then if you want to figure out the area, if f of a is 0, you just need f of b, right? So it plots the antiderivative on the right, and you can see as I move this around, the area changes. If I move to the right area, it gets bigger. Is that expected? What if I choose b equal a? What should I get? 0. If I move this way, this area is positive, but I'm going right to left now, which means I should get a negative answer. So by knowing the when you're at home doing this. Alright, so like here, if I plug in, if I choose A equal to 1, that means when they choose an antiderivative, they move it up and down until you plug in 1. So then, as I move B, the area gets bigger. And the area is the same as just plugging into the antiderivative. What's the antiderivative of 1/2 x? X squared, basically x squared. So they do 1/4 x squared, but then they move it up and down until the x-intercept is in 1. Alright, so you can see if you change A to be 0, that's like choosing C equal to 0. If I move A left, the area should be bigger, so I move it. So you can always see when I plug in like -3, -3 0. They move it up and down on the left. But then here, if I move this way, the area gets bigger. If I move this way, the area gets smaller. If I'm over here, the area is negative. Why is it negative? Because more of this is below the x-axis. Right? That's this whole idea. Once I know the antiderivative, all I have to do is plug in. Alright, so in the book it does say it must be continuous. That's not technically true. There are ways around this. You just have to be more careful. If it's not continuous, you have to be careful how you do the antiderivative and everything. But any of these technicalities you can actually get rid of most of the time. So now I want to do a bunch of examples for most of them. Any questions so far? This section is really saying just do a bunch of 4.4 and now plug in numbers. And the depressing thing is when you go to plug in numbers, it is not easy to plug in numbers. You'll do this much work to get an antiderivative, and then this much work to plug in two numbers and subtract. Okay. So first example. Let's find the integral from 1 to 2. Of x squared plus 5 over 2x. So what do I need to do? I could factor out the constant 1/2. I'm going to wait to do that. Does it look like a closure rule? No, closure rule, I would expect something down here squared, like a subtraction. So closure rule is not going to work. I don't have a way to undo closure. What are the only real techniques I have? I either need to recognize this as being the derivative from like a chart of derivatives, or I have the power rule. And I use the power rule here. So this is very different, and how we handle this problem would be very different than how we handle this problem. Even though these look, they're not much different, right? There's a major difference between how we solve this one and this one. What makes this one hard? This one is hard because I'm adding in the base. Adding in the base means I am stuck with that no matter what. But if I only add in the numerator and I have just one single entry in the bottom, what can I do?
Separate.
I have this one single fraction, I can break it up into two fractions. Here I can't break it up because I'm adding the base. So first thing I would do is write this as two problems. X squared over 2x, and then the integral of 5 would be what? X squared over x is the number x. And then here I can move the number of 5 halves outside. And have the integral from 1 to 2 of 1 over x. Does that make sense? Then what? What is an antiderivative for x?
1/2 x squared.
Half x squared, yeah, power rule. Treat it as x to the first power, add 1 to the power, I get 2, divide by 2. So this would be 1/2 x squared. And then the new notation, we say evaluate from 1 to 2. Instead of writing plus c, because I have a definite integral, I write this notation. Instead of writing plus c, just write this at the end. This is a shorthand way to say plug in the number 2, plug in the number 1, and subtract. What about the other one?
5 over 2 ln of x.
Yeah. What's the 1 over x is like x to the negative 1. Technically, you can't do a power rule for that. Because if you try to, what would happen?
You get
Negative
x.
1 plus 1 is 0. You can't divide by 0. So this is the one you just have to recognize. Which function had a derivative of 1 over x?
ln of
Ln
x.
of absolute value of x. And then I don't need to write plus c because I'm writing these evaluation values. Okay. What could I do at this step? So I need to finish that. Before I go too far, I might actually check to make sure I got the antiderivative correct. Why don't you maybe do that now? Off to the side. If you miss the antiderivative, is anything you do after this going to be correct? So you're going to do a lot of arithmetic and then get a number, flip to the back of the book, and it's not the same number. And you hate to be wrong because you missed the antiderivative. Like you want to be confident you plugged it in wrong, not you did everything wrong and then plugged it in correctly. So what is the derivative of, what's that, 1/4 x squared plus 5 halves natural log of x? This would be what? Bring the 2 down, 1/2 x plus 5 halves times 1 over x. Did that check? Yeah, this is what, 1/2 x, 5 halves, 1 over x. So, you can always check before you go too far. That part doesn't change. It's not equal anymore, but it is worth checking. So now what do? I need to plug in numbers. So x squared from 2 to 1 says 2 squared minus 1 squared. And then 5 halves, this would be natural log of 2 minus natural log of 1. As a note, technically this is 1/4 times 2 squared minus 1/4 times 1 squared. What did I do? I'm only plugging into x, right? I could distribute, or I could, factor out the 1/4. And then only plug into the x squared part. Helps a little bit on the arithmetic, do parentheses there. Alright, so what do I get? 1/4 times, what's that, 4 minus 1? Plus 5 halves times natural log of 2. What's natural log of 1? 0. So I get 3/4 plus 5 halves times natural log of 2. And that is an exact answer. That is the value for this definite integral that represents the sine area of this curve from 1 to 2. There's no reason these are going to work out to really nice numbers. to do a different example, or do you want to do this one, which I said would look entirely different with how you solve it? It's only the antiderivative that's different. Once you have an antiderivative, these play out the same way. Plug in numbers, subtract. Yeah, want to find this antiderivative or do another example? Alright, 2 people voted. Same way. It's like that argument, let's just stop voting now, this is taking too long, or stop counting now, it's taking too long. It takes too long to open an envelope, so let's just discard all those votes. 2 people said yes. Alright. How in the world am I going to find this antiderivative? We said the hard thing is the fact I'm dividing by x squared plus 5. So what do I do with it? Yeah, 2x, or yeah, the number on top messes it up. It does look like inverse tangent a little bit. If I didn't have an x here, this would be inverse tangent. It's annoying, these look almost the same. You change one, you put in x in one place, it changes the entire strategy. That happened here, right? I put an x here, I can do the problem. I don't put an x here, it's impossible. So that is the big difference when you do antiderivatives versus derivatives. Derivatives, I can always keep doing something. Yes?
You could maybe multiply the top and the bottom by the denominator to maybe make it so you can separate the numerator.
It'd make it worse. If they were doing limits or some other technique, I would say that might make more sense. So I like yours. You said inverse tangent if I didn't have an x here. But I do have an x here. So then the question is, how does that x change things? How does it relate to what's in the bottom?
Or maybe you could take the, take the 2x out of the numerator, put as 2 different, within the integrals, 2x times 1 over x squared plus 5, maybe?
Yeah, that'll visualize this. This is acting like 1 over x squared plus 5 times 2x. I'm going to write this one, but that is a good step to see it. What am I looking for here?
Oh.
Yes.
Oh, because 2x is the derivative of x squared plus 5.
We said that x squared plus 5 in the bottom is really messing us up. You take the term that's really messing you up, and then you look at it and see what is its derivative. Why would I want to know what is its derivative?
This is natural law of that.
Yep. So this is really integral of this times the derivative of x squared plus 5 dx. That simple.
So then it's ln of x squared plus 5?
What is the integral of 1 over u du?
1 over u, or ln of u?
Ln of u? Alright. What is the derivative? Yes. Of natural log of u.
1 over u?
1 over u times the derivative of u of x. Because I put the x there. These are kind of 2 ways of saying the same thing, and I don't know which one makes more sense. When I look at this, I have 1 divided by something times its derivative. What would happen if I take the derivative of natural log? I'd get 1 over something times the derivative. Or another way to see it is, this came from a chain rule, right? If this comes from a chain rule, what do I only need to look at? Just treat this like this is 1 divided by something. Just think of it as 1 divided by u. Instead of writing what the x squared plus 5 is, just write a letter u there. Do I know the antiderivative of 1 over u? Well, if I get 1 over u, that means the antiderivative was natural log, right? So you can write it either way. These are really kind of saying the same thing. One is start with the antiderivative, one is start with the derivative and find the antiderivative. But this template fits these, right? So what is the antiderivative? Instead of thinking this x squared plus 5 business, think of that as u. What's the antiderivative? Just natural log. And now I'm plugging in x squared plus 5. And then I'm evaluating from 1 to 2 instead of writing plus 2. Not everybody likes this one as much, so what should I do? Before I start plugging in numbers and everything else and flip this back to the book, excited that I finished the problem. Take the derivative. The more creative you are finding an antiderivative, the more you should definitely check before you move on. What is the derivative of natural log of x squared plus 5? It'd be 1 over x squared plus 5 times the derivative of the inside part. So I get 2x divided by x squared plus 5. Before you just start plugging in numbers, always make sure the antiderivative check. Alright, so that works, so now what? This is going to be the natural log of 2 squared plus 5 minus the natural log of 1 squared plus 5. So the natural log of 9 minus the natural log of 6. And you go to flip in the back of the book, and that's still that chart.
Simplify to
Back in the book likes to write just one number, so they probably combine logs. Like I said, sometimes you do more work on the plugging in and making it look right than you do on the actual finding that antiderivative. Yes?
Can you also go back to the u substitution?
Yes, you can. If we were in top B, I would only use u substitution. I'd never quite say recognizing this. U substitution would be, it would end up looking exactly like this. For those of you that want to use U substitution, it's one I'm not fully teaching, but I'm 90% teaching it. There is one catch. So I do want to do this once, because if you do this on a test, I would count off if you don't do this correctly. So I want to do the same problem with U substitution. So U substitution says, I don't like the bottom of this, call it x squared, or let u equal x squared plus 5. So then du dx is 2x. So du is 2x times dx. You're really not allowed to split part differentials, but formally we always do this when we apply this method. So the reason I care, dx is the same as 1 over 2x times du. So this says anywhere I have this, x squared plus 5, just write the letter u. And then anywhere I have dx, write 1 over 2x du. If I'm switching the letter u, I also need to get rid of dx, right? So this is almost correct. And now what happens? 2x dx is du. So I get 1 over u times du. Here's one question. What numbers do I put for the definite integral? This is where I'd come off if you do what you would be tempted to do. When I say 1 to 2,
You have to cite that.
those are x values, right? This says my bounds are from x equal 1 to x equal 2. What about u? Would u be 1 and 2 necessarily? I changed the entire problem, right? So the last step, if you ever do this, you'd say u of 1 is 1 squared plus 5, so I get 6. U of 2 is 2 squared plus 5, I get 9. So my correct bounds would be from 6 to 9, which looks entirely random. When you update to the letter u and transform your problem, you have to also update the bounds. For antiderivatives, we didn't do that, right? We found the antiderivative for u and then plugged the x's in. Here's the great thing. This is a number, right? Once I get this number, is there any reason to switch back to x? By updating the bounds, I get the exact number without ever having to rewrite the problem backwards or go backwards. Yeah.
Couldn't we still just plug x back in after we've done the
You
u?
could.
Like if we
But
wanted to, if we
you
wanted to
did,
not.
This line would be wrong if you write 1 and 2. So you end up making a mistake one direction and then making it again going the other direction.
Why don't you just do, for this part, consider it as an indefinite?
Yeah, nobody likes this. I'm getting natural log of 9 minus natural log of 6. So natural log of 3 halves. Because I plugged in my new number. Alright, so there is a third way to do this. Integral of 2x over x squared plus 5 is the same as doing the integral of 1 over u to u, which is natural log of u plus c, which is natural log of x squared plus 5 plus c. I found the antiderivative. So then the integral from 1 to 2 is the same as this value evaluated from 1 to 2. And then that would give me natural log of 3 halves. So I could just say, hey, over here find the antiderivative. Now I use the fundamental theorem that says plug in the bounds as like a second part to a problem. If I break it up into do an indefinite integral first, find the antiderivative, then I can go back and solve the problem I care about and make it a 2-step process. Yes.
Yeah, that's what I was basically asking you, but you said.
Here, if you do that, it's not right once these numbers are different, because this represents something. So, like, if you're doing this as one long string of equal signs, every equal sign needs to hold. This one only holds if you update the bounds. Here, I'm not doing a string of equal signs, right? I'm saying solve this problem, now go back and solve this problem. So it's kind of subtle. These are two different techniques for doing the same thing. It's all related. Usually when I write solutions, I always like to just do one long set of equal signs. And if you're doing one long set of equal signs for this, you have to make sure you update your balance. But you could always, fundamental theorem says find the antiderivative, then plug in. You can always make it a 2-step process. It's just now you have to do more structure work in this sense. Or be careful how you write it. Y'all regretting asking me to do that one? Alright, I have a few more examples. I'm going to switch. I'm not going to do these in order, so I want to talk about this one first. the definite integral, so this is technically number 4, from -1 to 1 of the absolute value of e to the 2x minus 1. So some of y'all mentioned it needs to be continuous or differentiable, it needs to be a nice function. In some sense, yes, in some sense, no. Yeah.
Can't we rewrite the absolute value as like the square root of that squared?
Yes, but it won't help you find the antiderivative. That's the way, in some sense, absolute value means piecewise. So, like, what would happen if I graph e to the 2x minus 1? Y'all clearly know this off the top of your head, right? Graph would look like this. We only have 2 minutes in class, the graph looks like that.
But
What does absolute value do? Well, that's what I don't know.
Like reflecting in the negative part, so.
Yeah, absolute value says it can't be negative, so what do you do when you have a negative? You make it positive. So my absolute value would look like that. Anywhere it was positive, I'd flip it over. But now what's my problem? So if I'm integrating from -1 to 1, I want this area and this area. So this has this type of shape. So there's a corner here. Technically, it's a continuous function. I can still find an antiderivative and do everything. But do we know how to find the antiderivative of something that has this weird little corner in it? Or is that one where we're like, oh, something strange happened there, I need to be a little careful? Like when we did when we did derivative rules, I didn't really touch on absolute value, did I? That changes things a little bit. So there's a nice way to do this. What could I do?
Split into variables.
Split it into 2 problems. When I got to x equals 0, something, my shape changed a little, right? So the idea would be solve this from -1 to 0. And then solve it from 0 to 1. Does that make sense? That kind of avoids this corner issue. Nice thing about integrants or integrals, we can always break it apart into multiple problems, right? You can split your bounds. And then the next line is, why is this nice? How would we want to get rid of the absolute value because I didn't really have good rules with the absolute value sitting there. How do I get rid of absolute value? What did I do over there for this case? When I'm from -1 to 0, what happened? I had e to the 2x minus 1, it was negative. So
You multiply by
value, I had
-1.
positive.
You
How'd you go from negative to positive?
multiply by -1.
Multiply by -1. If you multiply by -1, you get rid of your negative sign. So if I multiply by -1, what does this become? Really what that says is reverse your order or subtract. E to the 2x minus 1 is negative. If I do 1 minus e to the 2x, it's the same thing but positive. Or you can say put a negative in front, distribute it. Negative times negative gives me a plus.
Since you're trying to negative, you just switch the intervals.
Nope. All those stay the same. Because what am I doing? I'm here with absolute value. This function is the same as this function.
But only within those
But
bounds.
only if I'm between -1 and 0. This says only look at these x values. For these x values, this and this are the same. And then I go over here. And what do I do to get rid of absolute value for x bigger than 0?
Well, nothing because it doesn't change anything.
I literally just erase them. There's nothing to do. It was already positive. So from here to here, I get this. So I want to break this up into several little pieces. I want to solve this problem, and then I want to subtract and solve this problem. And then I'm going to add, solve this problem. And then subtract and solve this problem. There are lots of ways you can do this. I think I have a different way to write it. I noticed those. So what's the antiderivative of x?
X?
Or sorry, what's the antiderivative of 1?
X.
Which is why I said x. Alright. What's the antiderivative of e to the 2x?
1/2 e to the 2x?
Technically, 4 says this is a formula. If I was saying the derivative of e to the 2x, I'd get e to the 2x times 2. So my guess is going the other way, it'd be e to the 2x divided by 2. So if you check that this one is 1/2 e to the 2x, negative 1 to 0. So the derivative of this would be e to the 2x. Chain rule says multiply by 2, that cancels the 1/2. So it does matter. Always check your antiderivative before you do way too many things that might be wrong there. Alright, this one works out the same way. And then I would do minus x from 0 to 1. So what do I get? 0 minus negative 1 for this piece. Minus 1/2 times e to the 0 minus e to the negative 2. Plus 1/2 times e to the 2 minus e to the 0. Minus 1 minus 0. So I'm plugging the numbers and subtract. So I get 1 minus 1/2 times 1 minus e to the negative 2. Plus 1/2 times e squared minus 1 minus 1. So those go away. So I get negative 1/2 plus 1 over 2e squared plus 1/2 e squared minus 1/2. Did we mention plugging in is by far the worst part? Like, you think calculus is hard, but we stopped doing calculus when we wrote this number, or this line. Now all we're doing is arithmetic, and arithmetic is awful. Okay. So final answer, negative 1/2 minus 1/2, I get negative 1. So 1 over 2 e squared plus e squared over 2 minus 1. That area is guaranteed to be that. What if I had instead done the problem negative 1 to 1 of e to the 2x minus 1 dx? Would I need to worry about breaking it apart or anything like that?
Mm-mm.
If I get rid of the absolute value, this would just be 1/2 e to the 2x. So I know that antiderivative minus x from negative 1 to 1. So 1/2 times e squared minus e to the negative 2 minus 1 minus negative 1. So I get e squared over 2 minus 1 over 2 e squared minus 2. Why is that value looking at it quickly, why is that one less than the other one? So in this one, I'm adding this number. Here I subtract. Here I subtract 1, there I subtract 2. Why is my answer less?
Because the left part is.
Yeah. That first part would have been a negative contribution before. When I did absolute value, I made everything positive, so I'm getting the biggest possible area value. When I get rid of the absolute value, this was negative, which is why if I don't have absolute value, one, it's a lot less work. But I get a number that's smaller, because now I'm getting signed area. I could be above or below. All right, we're out of time. 4.5 is really a lot more of 4.4 of find the anti-derivative. You get 2 sections on doing